Okay, so in this session, we will study the relationship between those two variables again, the same relationship, but in this one, we will know that we will have two variables. One of those variables, we call it independent variable, or we can call it predictor also, okay, which is x. So x is the independent variable or predictor. And also, the other variable, which is the dependent variable or response variable, which is y. So now we're studying the relationship between two variables, x and y. So now in here, x will be the predictor and y will be the response variable or the dependent variable. So what we will try to do, trying to find the best line will fit the data we have. So we still, the first step when we study the correlation or regression between two variables is to find the relationship, right? So, but in this case, we will try to find the best fit or the best straight line will fit this data set. So remember, we did say as those dots get closer to the straight line, then we will have a strong correlation, or the relationship between those two variables will be high, okay? So we will find the equation of the regression line. So this is, we know, this is a straight line, right? This line is a straight line. And you know, any straight line, we have a function of that straight line. So it could be a, or let's say beta 0 plus beta 1x. Okay. The problem, the best fit or this line is invisible. So no one knows this line, but we will try to estimate this line using a sample. So we will find y hat, which is estimated value of y equal to b0 plus beta 1x. So now this value is estimated value of beta. And this beta b1 estimated value of beta 1. Remember, b0 and b1, those two values calculated from sample. So those two values will be statistic. And those two values, beta 0 and beta 1, both of them calculated from population. So those two values, we call them parameter, right? So those values parameters and B0, B1 statistics. So then this function that you want to find y hat equal to b0 plus b1x. Okay, so then we did say beta 0 is a statistic value, and we use it to estimate beta 0, and b1 estimated value of beta 1, and then this is the sample regression function. Function or equation, and this one is a population regression function. So we did say this straight line is invisible. No one knows that. A straight line, only one case we know that line if the relationship is complete. Okay, there's no error. Otherwise, no one know this line, but we will use this one, which is the best estimate for this. Again, we have some requirement to apply regression. The first one, we use random sample or simple random samples. Okay, and then also, before we start studying the correlation, we should do what? The scatter plot, and we see some straight line pattern. So if we find the scatter plot like this, then no need to study or to find the regression function. Also, if we have any outliers, should be removed before we start. Okay, so now here, of those errors, then we should remove those outliers. So for all x values, the corresponding values of y, they have normal distribution. Let me go back here and explain this maybe. So if we come here. So now the idea is what? So imagine that we have x, which is, for example, income. And y, how much you spend every month. So this is the income, let's say 1,000, and then we have 1,500, and we have 2,000, and then 2, like, and so on. And here for y, so for a specific sample of x, we have different values of y, right? Because not all people, they spend exactly the same amount of money. So for example, the first one, his income 1,000, but he spent 950. And then we have someone spend 900. And we have someone spend, like, he lives with his family and then spend nothing, 200. And so on. One, like, has to borrow something, money, and spend 1,200, and so on. And here too. And so on, okay? So the idea, the corresponding value of y, so if we do the regression like this, so the scatter plot will be something like this. And then we have, this is our regression line, okay? So those, the first condition, those data set here, they must have normal distribution. Okay, so let's go back and then we'll go in a second here. So this is why the first one, y must have a normal distribution. And then also we must have equal standard deviation. So now x will have normal distribution with the mu and sigma equal. So imagine that even if we have, so the standard deviation for all samples will be normal distribution, okay? And then for y here, sorry, so this will be for y, not for x. So all of them, they have the same standard deviation. So let me take the next step, and then we'll go there, explain them together. And also y will be on the straight line here. the same straight line. So let's go back to this one here. So now the first one, if we, so this is for example here, for example, this is true value, right? This is the correct value. But when we did estimate this value, we use some value here. So now this value is considered as y, and this is y hat. And this distance here, we call it error of estimate, okay? But now for every single value, so for this one, we did this one. So every single value we have to do the data, all data set Y, they must have a normal distribution, and this is the average. The Y bar must be for this observation here, X equals specific value, let's say 10, Y bar must be on the straight line. So for every single value like this, oops. For all values, we must have a normal distribution, and this is Y bar. And this one, which is sigma, will be equal for all data sets. So all those equal to sigma. So now this mu, let me just, this value, okay, mu, different, that's okay. But for sigma, all of them, they have the same sigma. So sigma here and here and here and everywhere will be equal to each other, okay? So now we could have like Y from normal distribution. They might have different mu, but all of them, they have the same standard deviation. The standard deviation will be equal for all values. Okay, so then might we get like this is different mu's, but we have the same standard deviation or the same variance. Okay, so this is the formula how we calculate B1, or we can use this formula. So if we don't have this value of R, we can use this one. B1 equal to summation xy minus n x bar y bar divided by summation x square minus n x bar square. Okay? So use this formula to calculate beta 1 and use this formula to calculate beta 0. Since now you will use this value here. Y bar already known and this one is already known. So start finding. So the function we are looking for, y hat equal beta 0 plus beta 1x. Okay? So this value calculated from here and this value calculated from here. This one, you can use this one, but this is complicated. So just only use this one to find the y-intercept. And this formula again is the same, the formula I did. So just when we divide this by n, and here n, and then here multiply by n. So this one will cancel this one. So beta 1 will be summation xy minus summation x divided by n, x bar, summation y divided by n, y bar, but we have n here, so we multiply by n. And here is the same. So divided by n and divided by n here, and then we multiply by another n here. This one will be square. So this will cancel this, will be summation x square minus n, and summation x divided by n square is exactly as x square. So it will be nx square. So you can use this one, which is much easier. When you find B1 and B2, round them up to 3 digits, okay? We can use technology to find correlation regression function, which is, you will see this one. So let's say this is the same example we did before, but this is using like 23 data set. So if we go to technology, what we did here, so this is the example with the, oops. This is when the sample size equal to 5. So if we find the function, we did find, this is the correlation function. This is the regression function, sorry. This one is the regression function here. Oops. This is the regression function here. Okay, so y equal beta 0 plus beta 1x, and we have beta 0 equal to this value, and we have y value equal to this value. So it, okay. Then, so y will equal negative 11.286 plus 3.643x. Which is, when we'll use the same idea, we will get this function. So now the idea is here, as x changing by 1 unit, y hat will change by as x, this function here, as x increase by 1 unit, y hat will increase by 2.49. As x increase by 1 unit, y will increase by 2.49. Okay? So going to technology, you will see the results here. For example, let's say stat disk here. So this is the y-intercept. So by the way, so when we find that this point is 0 and beta 0. So this distance is beta 0, which is y-intercept. And beta 1 is a slope. If you remember a slope from long time ago, it's y1 minus y0 divided by x1 minus x0. So if you take any 2 points in those in the straight line and take, so this one will be x1 y1, and this, the other one, it will be x0 and y0. So if you take x0 or y1 minus y0 divided by x1 minus x0, you will get the value of the slope. Okay. So now the regression line we did find is just an estimate. It's not the regression line, it's the estimate or the best fit of the regression line. Because we did say, I did say the regression line or population regression line, it's a line that invisible, no one can find or calculate this line, but we can estimate it. So this is y equal beta 0 plus beta 1x. This is unknown, but we did estimate this one using y hat equal to beta 0 plus beta 1x. Okay. And remember that as we increase the sample size, as this line will be closer to this invisible line. So the formula that you can use for beta 0, we did say beta 1 equal to summation xy minus n x bar y bar divided by summation x square minus n x bar square, and then beta 0 equal y bar minus b1 x bar to find those two values. When you did so, just plug those values in this function, beta 0 plus beta 1 x. This is the idea basically, okay? Okay, so this is, if we have the value of R, then we can use it. Otherwise, you can use the formula we did use before. Let me go here, and we try to do just small example here. For example, if we have X and Y, we have 1, 2, 3, 4, 5, and we have 2, 4, 6, 8, 10. So this is, if we do it like this will be perfect relationship. But let's change it a little bit. So it will be 3. So if y equal 1 plus 2x, okay? So it will be 3, and then 5, and then 7, and then 9, and then 11, okay? So now this is still perfect relationship, but let's change one of, let's do this equal, for example, 8, and let's do this one equal to maybe 12. So now the relationship is not perfect anymore, right? So if we do this one here, let's check the total here. Will be, if we take this one, let's keep this one too. This one, for example, was just a convenient number. So here we have 7, 15, and this is 8 too. What we have now? What we have at the total now? So we have 35 here. And we have here 15, right? So now what we want to do to find this function, y hat equal beta 0 plus beta 1x, okay? So the first one we'll find beta 0, beta 1, which is summation xy minus n x bar y bar divided by summation x square minus n x bar square. So let's start. We need x bar and y bar. So x bar equals summation x divided by n, which is 15 divided by 5, then x bar equal to 3. This is the first one. And then y bar equals summation y divided by n equal to 35 divided by 5, then this is y bar equal to 7, right? And then we need x square, and we need xy. So x square, 1, 4, 9, 16, 25, and the total, I believe, 55. And then xy equal to 10, 24, 32, and then 60. So if we add those up, equal 128, I think, if I'm not mistaken. So now we'll find beta 1 equal to 128 minus 5 okay, and then we have summation x squared, which is 55 minus 5 times x bar, which is 3 squared. Okay, and you can find this value here, and then use this value to find beta 0, which is y bar minus beta 1 x bar. Y bar equal to 7 minus this value times x bar, which is equal to 3. We will get this this value of beta 0. Okay, and then plug those two values here in this function. So this is the idea how to find the regression line manually. Okay. So if we did so for the first example we did, so we'll find this function. So y hat equal negative 3.37 plus 2.49x. So we did say as x increase by 1, y will increase by 2.4. Look to this example here. So if we use this example or find this function, as x increase by 1, then y will increase by 2. So if we did say like x 1, 2, 3, 4, 5, then if we plug just the values here, it will be what? Y equal to the first one 3, and then 5, then 7, then 9, and then 11. Look, if you look here, every time we add 2. So now this is the best line for this data set. So yes, here. So this is the best line we can draw, which is make the error as small as possible. We are looking for the error values, and this straight line will make the error as, so remember, I did say this is the true value, right? But when we did estimate this value, we use this one. So this is the estimated value. This is error. So when we add all those error together, or the squared error, we will get the smallest summation ever. The problem is what? Y minus y hat will equal, when we take the summation of y minus y hat, will equal to 0. Right? Because this error, summation of error basically equal to 0, because this error has a normal distribution. Error has a normal distribution. Okay? But the problem is what? The problem, those errors could be positive. Any values in the top here will be positive. And this error might be a negative value. For the error here is negative. And if we, so for example, for this one here, the error will equal to 0 because y hat equal to 1. Okay, or if we're gonna write it in exactly way, expected of y hat, expected of y at specific value of x. Okay, but now since this error could be positive, negative, or zero, when we add up those errors, we will get zero, which is will make the negative values will cancel out with the positive value. So then how what we can do to eliminate the negative values, just square. So now we are trying, the goal is to get this value equal to zero. But if we have this value equal to zero, then all those dots will be exactly on the straight line, which is not the case on most of the time. So now we will try to get this value closer to zero or make this summation as as small as possible. So now, and this line, this line will make this summation is as small as possible. So we cannot get a smaller value of squared error from any other line. So now when we make, so now, okay, we have this function. We got y hat equal a, sorry, b0 plus b1 x. We have this one. But now, when we want to try to make prediction, we have to judge this line first. Is it a good model or not? So if this model or this line is good, then we will use this one for a prediction. How? Just basically, if we have a new value of x, we will plug it here. That's it. Okay, so now for get back, if we go back to this example here, if we want to do prediction, so just imagine that we don't have this value, so 6 point, I don't know, 1, if we don't have it in our data set. So just what we do, we don't, this is unknown. So we'll use this function and plug 6.1 in that function. We will get this estimated value. Okay, I mean, sorry, this is for good if we have a good model. So if we have good model, number 2, we just plug x. But if that model is bad, then we will consider y hat equal beta 0. And we will consider, so we'll consider that's no effect here, right? This is 0. And this is equal beta 0. So if we consider beta 1 equal to 0, that means no effect, or no matter the value of x, the y all the time will be the same. Then, and we know beta 0 equal y bar minus beta 0 x, right? X bar, sorry. And again, this value equal to 0, then y hat will equal to x, sorry, to y bar. Okay, which is using the sample mean, which is y hat equal y bar. If good model, y hat equal to beta 0 plus beta 1x. So those the values we will, or those two functions we will use for a prediction. And also we should check the correlation, right? So if we want to use this this function for prediction, we must conclude that we have a linear correlation. If we don't have linear correlation, we will not use this function for prediction. So we have two things. We have estimation and we have prediction. So let's say X and Y. So let's say 1, 3, 5, 7, 10, or let's like this, 7. So now we don't, so, and we have here 3, 6, 4, 2. I don't know. Now, if we want to get here at 2, this value, we call it estimated value, okay? But if we want to get the value here at 9, which is out of the scope of this data set, this we call it prediction. So if we are in the range of X, we call it estimated value of Y. But if it's out of the range of X, we will call it prediction value, okay? And when we use this one for prediction, we shouldn't go really far from the highest value. So if we have 7 here, okay, we might say that prediction at 9, maybe 10, 11, maybe, I don't know. But we cannot say that, oh, okay, we use this function to predict if we have a value of X equal to 75. So for sure, this value will not be accurate. The prediction value will not be accurate if we go like much beyond the range of available value of X, okay? So now here, so we did find the function, okay? So if this function a good model, then we will use this for prediction or estimation. If it's not good, then we will use y hat equal to y bar. Good model, then you use the sample regression function. Not good model, then use the sample mean. So let's see this example. Use the same example we did to predict the Nobel rare for a country with chocolate consumption of 10 kilograms. Okay, so if we go to this example here, okay, so 10, first of all, 10 is still in the range or out of the range. So it's still in the range because we have 11, we have 9, we have 11 here, we have 10, right? So 10 in the range of our data set. This is 1. 2, we did conclude that we have linear correlation, right? When we did study the correlation, we did say, okay, we have a linear correlation between Nobel and chocolate consumption, I believe, right? So we have linear correlation too. Then we can say this is a good model. And then we can use the sample regression function to estimate or predict, if inside the range, we call it estimate accurately, to estimate at chocolate consumption equal to 10, okay? So yes, we did this function. Because we know this one is what? Good model. Why? Two things. Because we have R, when we calculate R, we did say, yes, we have linear correlation. And 10 is not far from or still is in the, still it's in the range. So what we do, we plugged in. We say y hat equal to negative 3.37 plus 2.49. That's it. And we will get the value, okay? But what about this one? B, predict the IQ score of an adult who is exactly 175 centimeters. Now, first of all, even though we didn't study the correlation between those two variables, now we have two variables, right? We have the IQ and we have the height. Do you think, is there really any relationship between IQ and height? So if you say, oh, okay, if you are 160 centimeter, then you will, or as you get taller, as your IQ will be higher. No, right? So we know, even we don't study, we know there is no linear relationship between those two variables, right? So since we conclude that no relationship, then we cannot use any function or the sample regression function to predict, right? For prediction, we cannot. So now in this case, since those two variables, that they have no correlation or no linear correlation, then we will not use the sample regression function. Then the best, what? We will use y equal to y bar. Y hat equal to y bar. So since this is a bad model, right? We cannot use y hat for prediction. Then we will use what? Y hat equal to y bar. So if we did say y bar equal to 100, then y hat will equal to 100. No matter. So now all the time we will use y hat equal 100. If I give you x equal to 150 centimeter or even 210 centimeter, it's the same. Okay. So for part A, we did say it is a good model. So we just we use the y hat function and just plug the value of x equal to 10 or substituting x by 10. But the second part B is not good model because no correlation between IQ and height. Okay. In this case, we will use y bar equal to 100. Okay. So that's it for today. Do you have any questions? Hello?
No questions.
Okay, sounds good. Then try to review this one, and then we will start tomorrow, I believe, to chapter 6. So see you tomorrow then.
Thank you, Professor. See you tomorrow.
You're welcome. Okay, bye-bye. Bye.